going to talk about the Hypercomputing design project, which is as Ken said, a large disciplinary project looking at research in the intersection of research on design, research on scientific modeling and simulation, and research on high-performance computing. Paul Amaral is our fearless leader, director, and principal investigator. That's me. And there's several other co-PIs. This is giving some notion of the scale of the project. That bunch of co-investigators, notice the type size getting slowly smaller. Faculty and postdocs, graduate assistants, and technical staff. It's a big project. In fact, if you read quickly before I took those slides off the screen, you notice that many of those people were listed as being associated with institutions other than Rutgers. HPCD is a national consortium, although it's the main body, main center of gravity, and the administrative centers at Rutgers. Including the corporations that are collaborating with us, we involve roughly 100 researchers. 3 universities, although Princeton has this year been inactive. And even within Rutgers, sometimes it's harder to get people to talk together within one university than just get them to talk to their colleagues in the same department in another university. We have people from computer science department, electrical and computer engineering, from mechanical and aerospace engineering, and from the CAPE Center, that's the 4 departments of units, and altogether 5 research groups in that. We also have 3 companies that are actually funding the subcontracts, and 12 companies that are not funded through the project, but are actively collaborating with us. And our money, DARPA, comes from DARPA. It's, as you can see, a very large amount of money, almost $8 million over 4 years. So what are we doing? Well, we're doing all sorts of different things that you can imagine by the number of people involved. Let's look at one very specific example to give you a flavor of the kinds of things that we think about. This, you should imagine as being as on the front of a jet engine. This is the air intake, the inlet. Imagine flying along at several times the speed of sound. And the air is coming in here, and this is a sort of cutaway view. It's going through this channel, and back here is where the engine actually is, where the blades that turn are, and the combustion happens, and so on. And the problem, the goal of this structure is to have a shape so that when the air comes in here, it's coming in at many times the speed of sound. By the time it gets here, it has to be going less than the speed of sound. But you want to have a high pressure here, as high as possible, and as even as possible pressure here. If the pressure is very uneven across this area, then it does bad things to the stuff downstream, to the rest of it. So the question is, how do you design this shape, the shape of this space here between the 2 pieces of metal to make that happen? And so here's an example from one of our simulations. These show, I believe, the pressure contours, and this is the point of the sort of backwards, the point of the image flying this way that chart pointed out here. And this area here is a blow up of this area between the 2 pieces of metal. I don't know how visible it is, but the dotted line shows the old contour. That was done by human designers, and compared with the actual contour, which is one that our programs did. And we've done this kind of thing in several examples and come up in each case with substantially better designs than current state-of-the-art designers are able to do, or equally good designs much more cheaply. And in fact, this has raised a fair amount of interest in the aerospace industry. For instance, Aerospace Shell, the French aerospace company, I believe, is sending an engineer from France to work here in the project here entirely at their funding cost for a year. More than a year. More than a year and a half. So that's an example of a particular design problem that we're working on. But so what? Why is this particular problem hard? Well, there are several reasons why designing that inlet is hard and interesting and noteworthy. First of all, it's computationally intensive. It takes a huge number of computer cycles to do that design. First of all, the space of possible shapes is, if you're being a mathematician about it, uncountably infinite. It's a set of shapes, not just a fixed vector of real numbers. Even realistically, there's a huge number of shapes that you might consider. And if you evaluate even a single shape, can take a large amount of computer time. It can take literally days of the fastest computers available. Okay. Well, when we're faced with hard problems, what do we do? Typically in computer science, one of the things we try to do is break a big hard problem up into a set of smaller problems that are a little bit smaller and therefore easier. And then put the solutions to those small problems together, make a solution to the big problem. That's called decomposition. But in this problem, it's very hard to find a way to decompose the problem. You can't design the front of the inlet independently from the back of the inlet. The design interacts too much. You can't design the outside independently from the inside. So one of our key tools for solving hard problems in computer science doesn't apply, or at least it doesn't straightforwardly apply. We have various techniques for decomposing things, but not at all in the obvious, straightforward way. Another reason why this problem is hard is that there are multiple conflicting goals. You want the pressure to be high at its back. You also want the pressure to be uniform. You also want the thing to be manufacturable. Okay. David's turn one? Oh, Ralph? So you have to find a way to design something that meets multiple goals that are sometimes conflicting and sometimes not. What are our ideas for approaching this? Well, here are some of the ideas. One very key one is to use multiple levels of modeling. That is, while the best simulators take several days to analyze a single design, they're also very fast simulators, and they take several minutes. Why don't we use those all the time? Why do we want to accept the ones? The ones that are much more accurate. So one of the key ideas is to combine slow but accurate simulators with fast but only very approximate simulators. And one of our key issues is how can a computer program know which ones to use when and for what answering what questions. Another major class of issues that we've looked at is what we call knowledge-based integration of simulators and optimizers. Simulators, the ones that exist, are largely designed to be used by human experts. If you're not careful, you can give them input. If you give them input that's not just quite right, you get output that's meaningless, garbage in, garbage out, or actually something that's not quite so bad as garbage in, crash, no answer out. So it takes the way they're currently used is that human experts use them. Human experts prepare the input, look at the inside if it makes sense, and throw it out if it doesn't try something different if it doesn't make sense. Putting that into an optimization loop, putting that simulator under control of a numerical optimizer, and taking human out of the loop requires building that expertise needed to run the simulator into the program. Both to prepare the input and to detect when something bogus is happening in the output. Also recover from failure, because even the best of these simulators that simulate complicated real-world systems like jet aircraft engines, even the best of them occasionally fail. They either give you no answer at all, they give you answers that, like negative masses or square root of -1 velocity, something like that. And your optimizer has to be prepared to deal with those. And the way it needs to respond to a failure depends on exactly why it was asking the question in the first place. So it has to be a little bit more self-aware as to, for instance, if the simulator is analyzing a candidate final design, and the optimizer thinks it has got a final best design, and it gives it the simulator says, ah. Well, then one solution is to start again, find another good design. If, on the other hand, the optimizers sometimes try to find the slope of the thing they're trying to optimize. And so they analyze 2 points relatively close to each other, and from the values of those 2 points, they calculate what the slope of the surface is that they're optimizing on. And if the simulator fails when the simulator fails to answer the question that the optimizer asks simply because the optimizer wants to know the slope of something, then the optimizer's response has to be different than if it failed when the optimizer thought it had a real answer. And if the optimizer is a human being, that's very simple. Human beings are smart. But if the optimizer is going to be a program, then it becomes much more complicated. But in fact, there are a whole bunch of areas, and here are some areas that HPCD is looking at, that are difficult and difficult to automate for similar sets of reasons. Inlet and nozzles for jet engines is a project on. We're working on the conceptual design of the aerospace vehicle, that is the overall dimensions, the wingspan, the length, and diameter. This is work on innovative design of surface ships. That's boats. And ships. We have a large part of the project looking at design of microprocessors. Particularly looking all the way from the highest level architect designing the instruction set, design of the gross structure of the machine, all the way down to the very deep, very fine details of the photolithography by which the chip is actually going to be manufactured. And the focus here, in addition to the other problems that I talked about with the inlet that occur in this time period as well, also is the issue of how do you tie together the knowledge about design that works at all those different levels of abstraction. How do you get information back and forth between the very low-level details of how things are manufactured, all the way up to the large-scale structure of how many registers the machine has, or what the instruction set is. Now, you might ask, and certainly people before they gave us the money asked, why do you have to do all this together? Well, there are a couple reasons. One of them is that to do this research requires combining expertise from a number of different disciplines. It has required artificial intelligence, parallel algorithms, computational fluid dynamics, at least in the case of the jet nozzle, the hypersonic inlet. And what's been most interesting to me is that until we got these interdisciplinary teams together, we didn't even realize the right questions to ask. We didn't realize that for instance, putting together an optimizer and a simulator would have the problems that it has, and that would be a major focus of our research. And certainly, not only after asking questions, you need an interdisciplinary group to figure out the answers as well. Furthermore, working on multiple problems in one organization, in one group of people that talk to each other, has led to a large amount of transfer between the different problems. Not only between the different kinds of aerospace vehicles, and not only between aerospace vehicles and boats, but also, interestingly enough, transfers between design of boats and design of airplanes on the one hand, design of microcircuits, digital VLSI circuits on the other hand. It's also led us to test the ideas. It's very easy to think you have a general idea when you apply it to one domain. It's only when you apply it to multiple domains that you really know. Now, working across these kinds of boundaries, institutional boundaries, discipline boundaries, is very hard. We found that, for instance, if we want to start up a project with collaborators in another discipline, it takes at least a year to learn each other's language, just so that we can talk to each other and understand what we're saying. It can take another year to build the software infrastructure, get the programs, and understand how to use them, to begin to do the research. So here we've got like 2 years of upfront investment just in getting to be able to start and get to do this. However, hard as it is, it's the only way to obtain our goals. The goal of the project, perhaps the most difficult goal is order of magnitude speed up in the time from an idea to a product. We also want to develop general principles of design. The vision here is that research in the areas of artificial intelligence and parallel computing, and also other areas of computer science, and research in computational science, things like computational fluid dynamics, structures, and things like that, can advance our knowledge of design with all the obvious economic and practical importance. And furthermore, the vision is that working on design provides a very good test bed, very good forcing to stretch our knowledge in the areas, the academic areas of artificial intelligence and computational science and other parts of computer science. To see a little more technical detail, you should go to Tom Elman's demo. Tom, what's the official title of your demo?
An interactive environment for engineering design.
An interactive environment for engineering design. And where is it? Somewhere on the third floor.
Follow the science.
Follow science. And also follow pointer to our website.